Welcome to qnawire.
Okay, so what we have here is a Newton's second law problem, but one with a time-varying force. So first important key piece of information is that we know what the mass of our rocket is, and that is 8 kilograms. Um, and we know the functional form of our time-varying force. So I'll actually go one step further to explicitly remind ourselves that this is a function of time. So I'm going to write it in the traditional way. F as a function of t is equal to some constant offset a plus a different constant b that's being multiplied by time squared. So what this means graphically is that we are going to get half a parabola. That's what this means. So we have, for graphing our force as a function of time, then we put time on the x-axis and then force on the y-axis. What this means is that we're going to get a parabola with some sort of positive offset, and the amount of that positive offset is going to be a. Sorry, that's a terrible a. And the reason why a is this value right here is because when time is equal to 0, well, then that second term vanishes and you're only left with a. So that is the graphical intuition we're going to be using here. Let's go ahead and dive right into part A, which is to find the constants of A and B and any wacky units that they might come with. So I think the easiest way to do that is to just use the information that's given to us. So now that we have our explicit function, we can say that the value of the force at time is equal to 0. It's going to be equal to A plus B, where we plug in that value for t, which is equal to 0, and we square it. So we know that 0 squared is 0. 0 multiplied by b is going to make that entire value equal to 0. So we are only left with a. But not only that, we are told that the value of this force is 100.0 newtons. So we can actually already go ahead and put a box around that because we successfully solved for that first constant a. And then we can do the same thing by plugging in the value for what's happening at 2 seconds. And then I won't include all the significant figures just for shorthand, but remember the 2 seconds there. So same constant a added to b, but plugging in 2 seconds with all of its glorious significant figures. And then entire quantity squared. That is going, we're going to assert that that is equal to 150 newtons. But before we even get there, I'm going to go ahead and directly plug in our answer from before, which is to say that the constant a is equal to 100.0 newtons. We still have that constant b. And if we evaluate the square that's occurring here, that gives us 4.00. And remember that the units also get squared in addition to the numerical value. So that has units of seconds squared. And then again, the given piece of information to us is that the left-hand side is equal to 150.0 newtons. All right, so we can now go ahead and do math to this. Subtract 100 newtons from both sides. Divide both sides by 4 seconds squared. And then at the end of the day, to 3 significant figures, get a value of 12.5. And again, it's going to have wacky units. Newtons per square second. Okay, so that is part A, and just because the text of this problem is so long, we're starting to run out of room, so we're going to insert a new slide. But keep all that in mind as we move on to part B, where we now, and then B is divided into two parts even further, part Roman numeral I, or Roman numeral 1. So now we want to know what the net force on our rocket is, as well as the net acceleration at time is equal to 0. So the subtlety here is that we have a rocket that we're launching from the surface of the Earth. So there are two forces acting on this rocket. That's the force that we just described and solved for, our handy-dandy parabola force. But there's also the force of gravity because we're dealing with a rocket. So we're going to go ahead and subtract the force of gravity because it is working downward, whereas our other force is pointing upward. So we'll just go ahead and keep this force of 0. And then the force due to gravity is going to be the mass of our rocket, which we said was 8 kilograms, multiplied by the gravitational acceleration near the surface of Earth. So just to give you some numbers, remember from part A, we calculated that, or it was given to us rather, that the force at time is equal to 0 is 100 newtons, and then our mass is 8.00 kilograms. And lastly, we have a gravitational acceleration to 3 significant figures of 9.81 meters per square second. Plug that into a calculator, and then you will get a force of 21.5 newtons. Okay, but this problem is not only asking for the net force, but also the net acceleration. So we're going to have to take that one step further and apply Newton's second law one more time. So the net acceleration at time is equal to 0 can be found simply by dividing the net force that we just solved for. The net force at time is equal to 0 by the mass. So what that means is that we take 21.5 newtons and divide through by 8.00 kilograms. Plug that into a calculator, and then get that our net force is equal to 2.69 meters per square second. Cool. So that was part Roman numeral I of B. So let's go ahead and draw ourselves an imaginary barrier, and then continue with Roman numeral 2. And in this part, we want to find the net force after 3 seconds instead of 0. So what that will look like schematically is sorry, that was terrible. Sorry, let's start over. So the net force after 3 seconds is going to be equal to that force we found earlier, also after 3 seconds, subtracting off the force due to gravity, because gravity is always the same. Okay, so what will that look like in terms of functional form? So I'm going to move my equal sign over a little bit just because we're running out of space. That's going to be A plus B with 3 seconds to 3 significant figures, oops, squared. Subtracting off that same force of gravity, applying Newton's second law, where that's mass times gravitational acceleration. And then don't mind me moving my equal sign over even a little bit more. So we know that the units will work out. So we'll omit units, but that gives us 100, add on 12.5, square the 3 to give us 9.00, and then take off 8.00 multiplied by 9.81. There we go. Plug that all into a calculator, and then you get that the net force after 3 seconds is going to be equal to 134 newtons. Great, and then of course we're not done yet because we also need to find the net acceleration, but as we saw earlier, this is just one more small calculation. We can start with that. 3 seconds is going to be equal to, applying Newton's second law, the F net 3 seconds, the mass going here. So we just found it, and that was 134. Technically, it was 134.02, and then the mass is still 8.00. So at the end of the day, and then I think I'm actually able to type things out, or not. The net force is going to be equal to, net force specifically at 3 seconds is going to be equal to 26.6. Well, that's a big. Oh, sorry, I'm jumping ahead of myself. That's the numerical answer for part C. Whoops. 16.8 meters per second squared. All right, that was a long part B. Had 4 necessary answers to it. Okay, so let's internalize that. And then lastly, do part C on a third slide. So this is part C, and I could probably write a little bit bigger since we're on the last part. All right, there's no net subscript on this one because we're in the middle of space and we're not subject to gravity. So we're only doing the acceleration of that force we found, that time-dependent force we found earlier. So that's going to be what's occurring at 3 seconds. That's supposed to be a closed parentheses, and divide through by mass. So what goes on top? Our constant A plus B being multiplied by the moment in time that we're at, which is 3 seconds, entire quantity squared, and then the mass being carried over on the bottom. All right, so our constant A, which is 100, added to our constant B, which is 12.5, and then evaluating the square to get 9.00, and then the mass on the bottom being 8.00. Okay, so here goes the answer that I blurted out earlier, which is the acceleration in the middle of space after 3 seconds being equal to 26.6 meters per square second. big box around that. Okay, now we're done.